And we can move on to the next speaker on the program, who will tell us about select configuration interaction. The floor is yours. Yeah? Can you hear us? Yeah.
Excuse me, can you see my screen?
Now, not anymore. Now, yes.
Okay, thank you.
Yeah.
Okay, thank you. So, hello everyone. First, I would like to thank the organizers for this nice workshop. And so the main goal of this work is to develop a selected CI algorithm to compact the wave functions in the presence of an explicit correlation factor. And so to do that, first I will introduce the general framework, and then the main idea of the transcorrelated approach and the theoretical framework of the perturbation theory for non-Hermitian Hamiltonian. In the next section, I will discuss the algorithmic and technical aspect of the developed selected CI algorithm. And before the conclusion, I will show a few results and applications. So so configuration and interaction is one of the most general ways to improve the Hartree-Fock wave function by adding a description of the correlation between electrons. But considering all the possible determinants in general is not possible, and for this reason, one must truncate the CI wave function according to some selection criteria, like for example, by selecting the most important determinants in the energy. And so an efficient way to recover the loss in correlation from the truncated CI wave function is by adding an explicit correlation factor tau, which depend on the inter-electron distances. However, once the correlation factor is introduced, so the most previous important determinants are not necessarily those obtained before. So the goal of this work is to introduce a selected CI algorithm that allows to select the most important determinants from the full CI space in the presence of the correlation factor. So if we incorporate the correlation factor directly in the CI wave function, we end up with a variational problem. But the price to pay is that the evaluation of the matrix elements involve 3NE, where NE is the number of electrons, dimensional integrals to calculate, for example, the matrix elements of the Hamiltonian. So an efficient alternative is to incorporate the correlation factor directly in the Hamiltonian via a similarity transformation to obtain the so-called Hamiltonian, transcorrelated Hamiltonian. And therefore, solving the Schrödinger equation where tau is included in the wave function is formally equivalent to solve a new differential equation where the standard Hamiltonian is replaced by the transcorrelated Hamiltonian Hׁ TC. And since Hׁ TC is obtained via a similarity transformation, so these two Hamiltonian share basically the same spectrum. And we can write the effective transcorrelated Hamiltonian without exponential of tau as the standard Hamiltonian, the standard electronic Hamiltonian, in addition to these two commutators. So the resulting shape of Hׁ TC involves a non-Hermitian two-body operator and a three-body interaction term. So in other words, the transcorrelated approach allows to reduce the complexity of matrix elements evaluation from n electrons to no more than 3 electrons. But at the other side, HTC is not bounded due to the non-Hermitian operator in the two-body term, and therefore an extra care must be paid to handle this properly, as shown in the following. So for HTC, left and right eigenvectors are different due to the non-Hermitian term in the two-body operator, and the right eigenvectors does not constitute an orthogonal basis. However, left and right eigenvectors together constitute a b-orthogonal basis. So in order to let the energy become stationary with respect to eigenvectors, it's defined in the following bilinear form. So this energy does not satisfy the variational principle. However, its functional derivative with respect to left function, for example, becomes 0 if the right function is the right eigenvector of HTC. So in other words, we get the right eigenvector as a solution of this stationary equation, which leaves the energy stationary with respect to any left function. So the same thing also applies to left eigenvector, but here we are looking for the right eigenvector. So the usual Rayleigh-Schrödinger perturbation theory is well known for the case of a symmetric Hamiltonian, but it can also be extended to any non-Hermitian Hamiltonian, provided that this Hamiltonian has a complete spectrum, which is the case for HTC. Therefore, given a reasonable zero order approximation of HTC, we can write it as the transcorrelated Hamiltonian as HTC plus some perturbation. Then we apply the usual steps of the perturbation theory, where the right eigenvector is written as a known zero order wave function plus an orthogonal quantity obtained by projecting on some orthogonal basis phi I. So in practice, this will be the determinants from the external space. And by Taylor expanding the coefficients and the energy, we get the first and the second order coefficient and energy with a similar formula. However, which is different from the symmetric case, is the presence of this left function here instead of usually the right eigenvector phi 0. So in this work, we choose the Epstein-Nisbet model as a zero order Hamiltonian, where we introduce the general left function chi instead of phi 0 here, and E0 and phi 0 are the zero order eigenvalue and eigenvector, and D alpha here are the determinants from the external space. So for this choice of H0, the first order coefficients are given by the usual formula, and the second order energy are given also by a similar formula. But again, the left function is not phi 0 now, but a general left function. And so if we generate all the external determinants, we can then the summation of its perturbative energy provide an estimation of the transcorrelated fuel Ci energy by adding E0, of course. So in order to implement the discussed perturbation model and perform the CI selection, we modify the CI psi algorithm to handle the transcorrelated Hamiltonian. So we start by solving the transcorrelated eigen problem on some initial space of determinants D0 to obtain right eigenvector phi 0 and E0. And furthermore, we have now to consider some choice for the left function chi. So in this work, we have tried two different choices. The first one is by considering chi as the right eigenvector phi 0. So with this choice, the zero-order Hamiltonian becomes very similar to the usual zero-order Hamiltonian of the symmetric case. And the second choice of chi is the left eigenvector chi 0 with the same eigenenergy E0. And of course, as one the second choice, as one can expect, turn out to be much more efficient, and we will see this after in the result. So then we generate all the external determinants, and we compute the second order energy of H1. This allows to estimate the transcorrelated FuCi energy by adding all these contributions. And then we selected the most important determinants with respect to some criteria. So in our case, we fixed the energy as a criteria. We found that this is more efficient than the coefficient, for example. And after that, we modify the right eigenvector and the energy E0, and we iterate over these steps until convergence. So now, in order to obtain the left and right eigenvectors of the ground state of the transcorrelated Hamiltonian, we propose an iterative dressing scheme without instead of using a non-symmetric solver, so this scheme restores the symmetry of the eigen problem, as we will see. For example, consider the right eigen problem of HTC. So the first step is to write the transcorrelated energy as H plus some extra term, and then by dividing this extra term by the coefficients of the previous iteration I minus 1, and multiplying by the coefficients of the current iteration, and using the previous wave function instead of phi, we derive this equation where here the equality holds on the convergence. So to summarize the algorithm here, so first we start with the solution of H, and we build this diagonal dressing matrix by computing these integrals. So we apply a symmetric dressing and then a symmetric Davidson to extract the new eigenvector, and we iterate over these steps until the convergence of the right eigenvector. So in practice, we get a good convergence in less than 10 iterations. And for the left eigenvectors, we can apply the same scheme also. Okay, so now the three-electron integrals. So the three-electron integrals are the main bottleneck of the transcorrelated formalism. To compute matrix elements with the three with this three-electron operator, one need to calculate this 9-dimensional integrals, where phi are the molecular orbitals, and this operator depends on the derivative of the correlation factor. But however, the pair electron functional of the correlation factor allows to factorize and reduce the dimension of integrals to no more than 6, which is usually computable. And but even if we are able to compute these integrals, storing this tensor becomes quickly expensive for large one-electron bases, and so we need to do usually some approximation at this level. So for the 0 degree and or 1 degree excitation between two determinants, only for indices of this tensor are different, and the Hamiltonian matrix can be computed exactly. But for double excitation matrix elements, we have employed two different approximations. So in the first one, we neglect the tensor when all the 6 indices are different, and this approximation leads to a N5 scaling in the storage instead of N6. Another approximation that we have tried also is to apply a normal ordering technique of the 3-body term on a reference determinant in order to obtain effective 1- and 2-body operators, which results in a typical N4 scaling. Finally, we neglect the matrix element with 3 degrees excitation. But based on the applications done in this work, we found that this approximation weakly affect the results and lead to a bias of the order of 1 milliHz usually. So the correlation factor chosen to apply the transcorrelated selected CI has this following shape, where Earth here is the error function and mu is a parameter which controls the depth and the typical range of the Coulomb hole between electrons. So this correlation factor allows to cancel out the Coulomb singularities between electrons, and it depends only on one parameter, which can be systematically chosen via expressions derived in the range-separated DFT framework for a uniform electron gas. On the other hand, it enables an efficient 2 and 3 electrons integrals calculations in the basis of Gaussian molecular orbitals, and all the elements needed to calculate the Hamiltonian matrix elements and to perform the transcorrelated selected CI are implemented in quantum package. Okay, now a few results. So as a first application, we consider the oxygen atom in the valence triple zeta basis. So on the left, we have the plot of the transcorrelated energy of the selected wave function with the usual 0 order Hamiltonian. So in green for chi equal phi 0, and the selected wave function with chi equal chi 0, which is again the left eigenvector. In blue, we have the energy obtained for the same correlation factor by using the transcorrelated FuCi QMC method as a reference to check the convergence. On the right, we have a similar plot, but instead of E0, we plot E0 plus the estimated second order energy, and again for the two choices chi equal chi 0 or phi 0. So in this calculation here, we don't see any important impact on the choice of chi on the energy E0, and both converge to the blue energy. However, if we see here, we see that the PT2 energy converge much faster when the left eigenvector chi 0 is used. Here the same plot, but for the neon atom in valence zeta basis. again, you have the same conclusion. E0 in the case is in both cases converge in similar way to the blue energy, and the second order energy bias and the second order energy has a better estimation for for chi equal chi0. So after this benchmarks, here the last application on the molecule in double zeta basis on left and triple zeta on right. So here we have the plot again of E0 and E0 plus E2 for chi equal chi0 and for chi equal phi 0. In blue we have an estimation of the exact energy to check the obtained results. But here, in contrast to the previous case, we see that for chi equal phi 0, both E0 and E0 plus E2 are not converged for 100,000 of determinants. However, for chi equal chi 0, results are very close to the reference energy. But we see again that the peak 2 energy leads to yields to an important improvement to the energy of the selected CI wave function and accelerate the convergence to the transcorrelated fuel CI limits. So for the triple zeta basis, we have the same conclusion, but we see also that the energy obtained using the left eigenvector is very close to the exact energy, which confirms that the impact of the approximation on the three-body level is very small. So to summarize and conclude, the transcorrelated formalism is an efficient framework to handle explicit correlation factors, since the effective transcorrelated Hamiltonian contains no more than 3 electron interactions, and its two-body operator can be chosen to cancel the singularities between electrons, which improve the convergence with respect to the one-electron basis. Despite the non-Hermitian nature of transcorrelated Hamiltonian, one is able to apply perturbation methods and therefore extend selected CI algorithms. In this work, we choose to extend the CI algorithm to the transcorrelated Hamiltonian, and the results show that this allows to compact the wave function by selecting the most important determinants. And now we are working on using 2 molecular orbitals basis instead of only one, where the right Slater-determinants is constructed on a right molecular orbitals, and the left Slater-determinant is constructed on a different molecular orbitals. So we expect that by doing that, this will compact more the wave function, the CI wave function. And in the end, I would like to thank you for your attention.
Thanks. Questions from the audience? Yeah, speak up.
This transcorrelated approach in general, we do it in our group as well. It has always conceptually confused me. So at the very beginning of the presentation, you showed that the transcorrelated Hamiltonian and the true physical Hamiltonian, they share a spectrum. And then at the same time, one is unbounded and the other one is not. So I'm aware of the proof that the transcorrelated Hamiltonian shares eigenstates with the true Hamiltonian, but are they always, it is very hard for me to believe that they are always identical.
Yeah, yes, right. So you are right. H and HTC as operators, it shares the same spectrum, but when once projected in some finite basis, we will not find the same eigenstate, and so we will find the same eigenstate and eigenvectors in the limit of complete basis in the limit of complete basis set. So So right, when we work in a finite basis, we will not find necessarily the same eigenstates.
And then a second aspect is the non-Hermiticity, which I personally find very frightening, because if I ask you to do something very simple, such as unitary time evolution, which is fundamental to quantum mechanics or projection operators, you lose the entire physics in that ansatz. So as long as you look at your Hamiltonian as a matrix and get eigenvectors of that matrix, that's fine, that's linear algebra. But we should not forget that there's physics behind these operators and they are continuous objects. So for instance, how would you do time evolution? How would you rotate your wave function without changing? Is there literature on this?
So I think I understand your question, but so we end up with a in this case at least we end up with non-Hermitian Hamiltonian, because we impose some shape on the wave function which is not necessarily the exact wave function. So how we can understand this exactly from the physical from a physical point of view, I don't know, but technically this will be allowed to evaluate matrix elements in an easy way, relatively, and we're still able to, but we still able to do usually all the optimization or all the method that we can do for the usual Hamiltonian, as for example the perturbation theory. So we can figure out how we get a stationary equations instead of the variational equations. So we can do the I believe that we can do the usual optimization within TransCorrelated Hamiltonians.
And the last follow-up, if I'm allowed, this bivariational principle basically that you outlined in the following slides, that is it's quite popular, and I believe it originated in coupled cluster theory. Did you investigate that connection?
Sorry, can you repeat the last question?
Basically the energy function that you wrote down, that is the bivariational principle. It commonly occurs in perturbation theory, and it can be used to elegantly derive the Wigner 2n+1 group. It stems from coupled cluster theory. Did you investigate the connections between your non-Hermitian Hamiltonian and bivariational coupled cluster?
No, but I know that TransCorrelated also is combined usually with coupled cluster, not only with CI method. So yes, it's feasible. There's some people who do that.
Thank you very much.
Thanks. And